previous lesson, we introduced the Pauli matrices, and now we have everything to start a conversation about quantum logic operations and quantum calculations. As we have already said, the operation of each classical computing device can be described either using the Turing machine or using a switching circuit. We can say the same about any quantum computing device, only now we have to use either a quantum Turing machine or a quantum switching circuit. We are more comfortable with switching circuits, so we will not consider the quantum Turing machine. As it was in the classical case, any quantum switching circuit, in contrast to the Turing machine, is finite. It consists of a certain limited number of wires and logical elements. Only now, the wires do not transfer the bits, but qubits, and accordingly, the logical elements perform quantum logical operations on these qubits. Note that in accordance with the Landauer principle, which we formulated earlier, quantum logic elements are initially made reversible. Otherwise, the release of the excess heat during the destruction of information could purely physically spoil them. In addition, this condition is a specific of quantum computing. So, if we have a set of qubits in the pure state at the input of quantum computer, then at the output of quantum computer, we also need to get a set of qubits in a pure state. A transformation that makes one state vector from another and at the same time preserve its norm can only be unitary. Such a transformation corresponds to a reversible physical process. From the point of view of mathematics, each quantum logical operation has its own unitary operator. Let's move on to the consideration of the elementary single-qubit logical operations and the corresponding quantum logic elements. It will be convenient for us to consider the qubit as a superposition of the eigenvectors of the Pauli matrix sigma 3, which is also called the computational basis. Recall that we denote such state vectors as 0 and 1. In addition, in some cases, we will also use the Pauli sigma 1 matrix eigenvectors called the Hadamard basis. We denote such state vectors as plus and minus. The choice of the basis is very important because with it we always associate the basis of some measuring device. According to the Copenhagen interpretation of quantum mechanics, when discussing any characteristics of the physical system, one must always indicate which instrument they were obtained by. We already talked about this when we discussed the so-called EPR paradox. Therefore, as the first logical element, let's consider the element x, which is similar to the classical element not. Under the action of the element x on the vector state 0, it's changed to the opposite and becomes the state vector 1. On the contrary, under the action of x on the state 1, we get the state vector 0. This is an analogy with the classical element not. However, in the quantum case, it is important to know not only the effect on the basic element 0 and 1, but also on the superposition, since in the general case, a qubit that arrives at the input of an element x can be in superposition state. Thus, if the qubit at the input of the element x was in superposition, alpha multiplied by the state vector 0 plus beta multiplied by the state vector 1, then at its output we will already get the superposition alpha multiplied by the state vector 1 plus beta multiplied by state vector 0. Such an action of the element x on the states 0 and 1, as well as their superposition, tells us that the mathematically unitary operation corresponding to this element will be identical to the Pauli matrix sigma 1, or it is often denoted sigma x. Schematically, this element will be denoted as the Latin letter x. The next element that we consider is the element z. When the element z acts on the state vector 0, it does not change it. And when the element z acts on the state vector 1, it also does not change it, but the minus sign appears in front of it. That is, the state vector 0 and the state vector 1 are eigenvectors of the operator corresponding to the element z, and +1 and -1 are the corresponding eigenvalues. Recall that an arbitrary state vector is defined up to the absolute phase, that is, to the exponent multiplier in front of it, to the degree I multiplied by phi, where I is the imaginary unit, and phi is the absolute phase. If phi is equal to pi, then the exponent will be equal to -1. Thus, since the minus is associated with the common phase, it does not affect anything and can be omitted. However, a completely different situation arises if acted by element z on superposition. In this case, the minus will already be associated not with the absolute phase, but with the relative phase between the superposition members. If the qubit at the input of the element z was an alpha multiplied by the state 0 plus beta multiplied by the state 1 superposition, that at its output we get the superposition alpha multiplied by the state vector 0 minus beta multiplied by the state vector 1. Naturally, such a transformation is already significant. And since the element z changes the relative phase between the terms of the superposition, it is also called the phase element. Note that if we work in the basis of 0 and 1, that is, eigenvectors of the Pauli 3 matrix, then the transformation performed by the element z does not have its classical analog. In classical calculations, we simply do not work with superpositions. However, if we choose the Hadamard basis plus and minus, it turns out that the element z will be similar to the element x or the element naught. When it acts at the state vector plus, it will turn into the state vector minus, and the state vector minus is turned into the state vector plus. Their superposition will look similar. The transformation using the element z will be identical to the action of the matrix sigma 3 or the matrix sigma z. We will denote such a transformation in the form of the Latin letter z. The next transformation we consider is the y transformation. We will not dwell on it in detail, since its action can be reduced to the action of x and z transformations considered earlier. This is due to the fact that the Pauli matrix sigma 2 on sigma y will respond to the y transformation, which, as we learned in the last lesson, can be expressed in terms of the products of the matrices sigma x and sigma z multiplied by the imaginary unit. When acting on the superposition alpha multiplied by the state vector 0 plus beta by the state vector 1, we will have to swap 0 and 1 and replace the plus sign with a minus sign, as it's shown on the slide, and then multiply the result by an imaginary unit. If this imaginary unit turns out to be related to the absolute phase, then again we can ignore it. In the previous lesson, we defined rotation operators around some given axis at the angle phi. As it was shown, Pauli matrix is associated with rotation around the corresponding Cartesian axis 1, 2, or 3 on x, y, z, at an angle pi around it. Earlier, we introduced the Bloch sphere to visually describe the state of the qubit. Now, we want to consider this concept not separately, but together, for a description of the introduced logical operator. On the slide that you see now, the logical operator x, y, z acting on the state vector psi are presented as rotations around the coordinate axis of the Bloch sphere. Let's recall that we associate the positive direction of the z-axis with the state vector 0 on the north pole of the Bloch sphere, and we associate the negative direction of the z-axis with the state vector 1 at the south pole of the Bloch sphere, and so on. It turns out that the logical element x rotates around the x-axis at the angle pi. For example, if the psi-state vector for our qubit looks to the north, that is, coincides with the state vector 0, under the action of the element x, it turns around the x-axis and it's at the angle pi, and we get the state vector 1. That is, from the north pole of the Bloch sphere, we move to the south pole. We'll get a similar situation for other elements. For example, in figure B, you can see that when the element y acts on the state vector psi 0, we get, as a result, the vector psi 1 by simply reflecting the vector psi 0 relative to the y-axis, while the plane in which vector psi 1 lies and the y-axis, in this case, simply coincides with the picture plane. The next very important logical element that we consider is the Hadamard element. It is sometimes also called the Walsh-Hadamard element. At the slide, we see a schematic representation of the Hadamard element in the form of the Latin letter H, as well as its matrix representation. The most important properties of the Hadamard element is that it converts the computational basis into the Hadamard basis. So, for example, when the Hadamard element acts on the state vector 0 from the computational basis, we get the state vector plus from the Hadamard basis. And under the action of Hadamard element on the state vector 1, we get the state vector minus. Using the explicit form of the Hadamard operator, or the fact that it converts the state vector 1 and 0 into state vector minus and plus, and the states plus and minus into the state vectors 0 and 1, it is easy to show that the square of the Hadamard operator is equal to the identity matrix. Another logical element which we briefly consider is the phase element T. The slide shows an explicit matrix form of the corresponding operator in two different forms, and in the second case we again took out the phase factor, which in many cases will not play any role at all. The action of the element T could be reduced to a change in the relative phase of the superposition terms of pi to 4 and not on pi, as well as the case of the element that. An important property of this logical element is that together with the Hadamard element, they form a universal set of one-qubit elements. That is, any other logical element can be expressed through these ones. And finally, the last but no less important element of any switching circuit is the element designating the measurement. This element implies some measurement procedure, that is, interaction of the quantum object with a classical microscopic device. The basis of this device contains orthogonal macroscopically distinguishable states, that is, when measured as a result of the reduction of the state vector, one of them will work and we will know exactly which one. For example, we can see exactly where the electron deviated in the external electromagnetic field if we measure the projection of its spin using Stern-Geller device. Or, in the case when the qubit is implemented on photon polarization, separate one polarization from another using a polarizing dividing plate, and then using photon counters for each of them to find out what kind of polarization the photon received as a result of the reduction. That's all for now. Thanks for your attention.